So there's this idea called mean free path, and that is the average distance that a molecule can travel freely without running into something. So the free path for any given particle is going to be different, right? This one went this far before it ran into something. This one went this far. And so, over here, this was a small amount before it ran into something, but you could look at the average. And the average free path length, or the mean free path length, is going to get smaller as the pressure increases. So if I squeeze all of these particles closer together, you can imagine they're going to run into each other more often. The free path goes down. If nitrogen was the size of a golf ball, it would get to go about 40 feet between collisions. So those gas particles are moving just by themselves most of the time. The process by which gas molecules spread out from high concentration to low concentration is called diffusion. Heavy particles at the same kinetic energy are going to be moving more slowly than light particles, right? So the rate of diffusion is going to depend on the mass of the particle. The process of a gas escaping through a small hole into a vacuum is called effusion. So diffusion and effusion, those are different things, and you'd probably be a good idea to put those on flashcards and learn those words. So the rates of diffusion and effusion are both related to the velocity of the gas, root mean square velocity. So if we have the same temperature, it means that the rate of gas movement is inversely proportional to the square root of the molar mass. And the book goes through the whole derivation of this, which I'm not going to do. This is the bottom line here. So for two different gases at the same temperature, the ratio of their rates of effusion is given by this equation, and I'll give you that equation also. The rate, or the root mean square velocity for A, was the square root of 3RT over capital M. And so that's where this comes from. And then if we're dividing by this, the molar mass for B ends up in the numerator. So helium escapes from a balloon faster than air because smaller helium particles effuse faster than nitrogen molecules, which is what air mostly is. So if you have two balloons, one filled with helium, one filled with air, same kind of balloon, same conditions, the helium balloon is going to get small faster. And it's not because of the sizes of the holes in the walls of the balloon. It's because the helium atoms are zinging around faster and they hit the holes more frequently. So this is kind of a mind-boggling thing. So here we have a box, and we've got essentially nothing on this side, and we have a gas on this side. And in this wall, there's this one little hole. So these gas particles are zinging around, bouncing off of each other and the walls. They are going to stay on that side, though. Here, it's a vacuum, basically. And you might think, well, it's going to suck the gas out. Or the gas here from pressure is going to go whoosh and go through the hole, right? Because that's what water would do. No, these are bouncing around. They're only going to go through the hole if on their path they hit the hole. So zinging around, it was like, if we were throwing balls around and we had the door open, the balls are only going to leave if they happen to get thrown through the doorway, right? They're not just going to fall out of the door. Because small particles move faster, they're going to have more chances at hitting this hole, and they're going to get through the hole faster. That's effusion. Find the ratio of the rates of effusion for hydrogen to krypton. So we want the rate for hydrogen, the ratio to the rate for krypton. That is equal to the square root of the molar mass of krypton divided by the molar mass of hydrogen. In the root mean square equation, those molar masses had to be in kilograms. Here we have a ratio of one to the other. We can put them in kilograms, but the conversion factors cancel out because all the units end up canceling out. It kind of does matter which one starts at the top. So here it's asking for the rate of hydrogen, the ratio of hydrogen to krypton. So I want to put hydrogen on top and krypton on the bottom. And then they're going to be opposite on the other side, because this is A and that's A. This is B and that's B. So I need their molar masses. Krypton, 83.80 grams per mole. And if it bothers you that it's supposed to be in kilograms, we can convert that. And down here, I've got the molar mass of hydrogen. It's H2. It's supposed to be 6 grams per mole. And I can convert that to kilograms as well. And then the square root. So those two conversions cancel out. The grams cancel, the moles cancel. I get a ratio which has no units. Square root of 83.8 divided by 2.016. 6.447. Well, this is related to the root mean square velocity equation, and where capital M was kilograms per mole. Here we can use grams per mole, but some people find that confusing, and so you can convert to kilograms, but I'm also showing you that it doesn't matter. So hydrogen will effuse 6.447 times faster than krypton. Yeah. It's not a percentage, it's just a ratio of this one is this many times bigger than the other. Yeah. 6.447 to 1.